eventually you come to these two equations that would come from Edinger et al. The surface heat transfer coefficient, and you know, it isn't apparent to you, but this FW has something to do with wind. So, you know, and you can just imagine when the wind blows strong, there would be a lot of transfer between the water and the atmosphere. And if there's no wind, the transfer would be minimal. So once again, you want to have confidence in your wind record. You know, you don't want to have drift in your wind record. To the best possible extent, you want to get the wind over the water surface at the right height, that sort of thing. And then the equilibrium temperature. I won't go into every one of those terms, but there's the equilibrium temperature. And it's detailed in this chapter, and once again, the program will deal with this for you. You really don't need to, but I just want you to have some sense of what goes on inside the program. And let's see. Go ahead, Jim.
You're not finished with the heat part, are you? I mean, the lecture part of it.
In about 10 seconds.
Okay, because I may have a question. I didn't want to anticipate before you got to it.
Okay, well, you know, there's the input to the HEX program. So those are, you know, I guess the date, and there you go. You know, it's not labeled, but those are the things that I told you need to input to the program. And the program itself, we'll look at this one. There's the output. This is formatted just as is necessary for the water quality model. The only thing is you're missing 2 or 3 title lines. But you know, this is exactly the file that is read into the water quality model as the MET file. And
I have a question. So, do you read the pressure, air pressure?
Not necessary.
So you have this DO saturation equation that calculates that's related to.
What we say is that pressure at the water surface is 1 atmosphere, so we don't have to worry about it. Okay. And I guess today is a high or a low or something, but you know, that's just levels of detail we're not going to worry about. What else is the last one? Just because, we'll open this one up, edit with Notepad. And this is your program. So you read heat exchange input, you output heat exchange output. There's a line that tells you what you're reading in, year, month, day. Multiply the wind speed by 1.5, just as I mentioned to you, and from there on, it's just a Fortran. It's my translation of those equations that came out of Edinger. Sky cover in eighths, you know, so we take the sky cover and divide by 8 to turn it into a fraction. So, with that, what Jim, you said you had a question?
Yeah, actually, sorry, 2 questions. So, does the, you know, now that you're trying to calibrate, I would imagine that the model does very well in the open waters because it's got the wind, and the tributaries might be a little bit more challenging given canopy and wind sheltering. Is that true, or does the model actually do pretty good in the tribs?
I think it does well.
It does pretty good.
Probably because even the places, those small tribs are tidal, you know what I mean, so the water's constantly going in and out.
The other question is, when you apply the solar radiation, is it all being applied into the surface layer, or do you distribute the heat because of, you know, the extinction coefficient may distribute it at a couple of different levels?
It's all applied to the surface.
It's all to the surface.
Yeah.
So at times you may overheat the surface a little bit, so that could be a calibration issue. Or because I know the reason I asked is because the hydrodynamic guys at our shop did the same thing. It was always in the surface layer. We got overheating, and then they started distributing it in depth, and it made some differences, but it may be in shallower systems that we deal with every once in a while.
You know, it's people I worked with at the court had the same criticism or something that you have, and I think two things. In lakes, what you're talking about is very important.
Right, right.
Okay, in a lake where it's nice clear water, the solar radiation gets transmitted, you know, to considerable depth. So the solar, it could be heating that lake to considerable depth. And my argument was, well, the Chesapeake Bay is so turbid that the penetration of solar radiation, our surface layer is actually 2 meters.
Oh, that's true.
So I said the penetration of solar radiation below 2 meters, I'm not going to worry about it. So if you do this in a lake or really crystal clear water, or if, I don't know, Florida Bay or something, you might think about that. But for the bay, I don't think it's a concern. Go ahead.
So the surface layer is like 2 meters deep, and you're saying the light is almost gone after 2 meters.
Yeah.
Will that cause any problems when you calculate phytoplankton?
Okay. Well, the model extinguishes light with depth. So let's say the phytoplankton in the second layer. What the model does is with depth, it computes the radiation at every one of these, and then it averages it over this box. So this box, what we do is we have the radiation here, you know, anyhow, the radiation that's available to the phytoplankton diminishes with depth.
Right. It averages them over the box, it doesn't take a lot?
It averages them in that correct fashion, but it does average them. It's not an arithmetic average, it's actually...
Gotcha.
Okay. Last chance.
Can I ask big picture questions?
I'm here, you know. Go ahead, seriously.
What kind of formal analysis of the model errors have you guys done?
Formal, we've not done any. Well, actually, I take that back. We have. I've computed traditionally 2 model statistics, the mean error and the absolute mean error. Mean error is the arithmetic difference between observations and model. And basically, it's high or it's low, you know. So there is the mean error. And again, so now mean error, you can tell the chlorophyll on average is high or low. And we do that by system. You know, we don't do it overall. We would do it for the...
sort of model bias.
Yeah. And then the absolute mean error is more or less analogous to the root mean square. It's the difference, it's the average of the absolute difference. So it's sort of a measure of accuracy. In fact, it is a measure of accuracy. Every observation, take the absolute mean difference, because I want it to always be positive, then take the average. And those are reported in the manual. I don't have them. The report for this phase of the model, those are in there, and they're actually compared to other phases of the model. So you can see how it's moved, if any, and you can also, then there is a discussion of what these errors mean, how we interpret them, you know, why specific parts of the bay were better or worse in calibration and that sort of thing.
Have you looked at the trends in the model error with time or with temperature or with...
Well, we look, when you say with time, we've looked at them for different phases of the modeling. And the reason I do those statistics, interestingly enough, is those are what we used way back in like 1992 for the first model. So we actually have a record of how those 2 statistics have progressed through to the latest phase of the model.
I know you believe you understood what you think I asked, but I'm not sure you realize what you heard is not what I meant.
Okay.
So what I meant was, if I look at the errors and I try and plot them against, say I'm looking at the chlorophyll errors and I plot them against the concentration of chlorophyll, is there a change in the errors with concentration?
We've not done anything like that. Kyle?
So just again to clarify, the only way that heat can be transferred to cells below the surface layer is through interactions with the surface that gets solar radiation, and then at the boundaries. Is that right?
The subsurface cells?
Yes.
The only way subsurface cells can get heated or cooled is either it's a boundary or they mix with the surface. It's not the irradiance passing through the surface, it's the surface has a temperature and this diffusion and advection, so the one below it would be temperature would be diffused and advected. Okay, it's caffeine and sugar, and then we're going to pass the baton to Richard, who's going, oh, wait a minute, we got no more, there's no caffeine and sugar? Don't
There's definitely caffeine and sugar.
Oh, okay.
But just wanted to make the point that the watershed model, the Chesapeake Bay Program watershed model, drives Carl's model, but also we've had a number of people with other models that have been interested in getting the outputs of the Bay Program watershed model. And so Gopal is the expert there, and actually Kyle did that for a few years while he was at the Bay Program, and now he is a receiver of model output again. But it's sometimes interesting to compare what Carl's model is doing and what other models are doing with the same inputs. And so I think there's about 4 or 5 different models that are driven from time to time by Bay Program models. So that is available.
Okay, now caffeine and sugar? Yeah. Okay, let's do it.